So today we're going to talk about part 2 of failure probability estimation. Okay, so now let's get into it with a little bit of a recap of importance sampling. So I realized the last time there was kind of a lot of distributions going on, a lot of, like, different distributions that mean different things, samples coming from different places. So what I want to do is try to kind of boil it down to the minimum things that I want you to take away before you at least maybe go back through and read the book. I understand you're probably studying for the quiz now, so maybe you haven't read this chapter yet. But I want to kind of break it down to the kind of minimum set of things that I want you to take away at first, just to understand the rest of this lecture, so we're all kind of on the same page. Okay, so we were talking about this thing called importance sampling, and the whole reason that we wanted to talk about it was because we had kind of this direct estimation algorithm where we would just sample from the nominal trajectory distribution and estimate the probability of failure from that. But then we realized that if failure events are rare, then we might not even get any failure samples. And so that's not going to work so well. We're just going to have like an estimate of 0. And we also saw when we looked at like the variance, I showed you the formula for the variance of the direct estimation estimator. And we saw that as the probability of failure decreases, that variance increases. So basically the estimator will get less and less accurate as our probability of failure decreases. And the only way to fix that is to get more samples, but we might require like billions and billions of samples. So this could be very inefficient. So we said, okay, let's try to do something else. And the something else that we do is that we just want to sample from a different distribution that we call Q of tau. We call this a proposal distribution. And the idea is that we want this distribution to hopefully produce more failures than the nominal distribution. So in this case, for example, we picked this Q of tau here, and we actually were able to sample some failures when we sampled from this distribution. But then we're like, well, we still want to estimate the probability of failure under this nominal distribution. So we can't just, take the number of failures here and divide it by the total number of samples, because that will give us the probability of failure under this distribution. And so what we actually need to do to get the probability of failure under this distribution is we do a similar thing, but we just have to weight all of these samples based on their likelihood under the nominal distribution. So we saw that those weights were basically the likelihood under the nominal distribution divided by the likelihood under this proposal. Okay, and then what I was kind of trying to show you in that Pluto notebook was that some proposals work better than others. So it really matters what we pick for this proposal distribution. So what this is showing here, this is a graphic from the book. We have our nominal distribution is just this simple Gaussian again, where the failure threshold is -2. And we can see how that does. This is kind of, again, we're plotting the estimation error. So we want to be lower on this plot, ideally. And then we want to have kind of lower spread among our estimates, because that means on average we'll be closer to the true estimate. Okay, and so then this is kind of the performance of this direct estimator. And now we could see if we shift our proposal over to be this blue proposal here, we're kind of now centered around the very high likelihood region of the failure distribution, and we were able to get a much lower variance estimator that's also much more accurate. But what I also want to show you is that it is possible to pick a bad proposal. So for example, if we pick this orange proposal here, it's now assigning high likelihood to kind of low likelihood failures. So we are going to sample failures with it, because anything to the left of -2 is a failure. But we're not really assigning it to failures that have very much probability mass. And so we could actually end up doing worse than our direct estimator. So it really matters what proposal we pick. And that's kind of the point I'm trying to drive home here, which is that picking a good proposal distribution is very much critical to success with importance sampling. And so then we went on to look at, say, can we find what the actual optimal proposal distribution is with respect to the variance of the estimator? So I didn't derive this, but I just showed you this is actually what the variance of the importance sampling estimator looks like. And we went on and we showed that if we plug in this particular density for Q of tau, then this variance becomes 0, and we get the estimator that has 0 variance, and this would be optimal. But then we said, actually, this is the failure distribution. And so, on the top here, we have kind of the unnormalized failure density we've been used to seeing. And then we said that the normalizing constant for the failure distribution is just the probability of failure. And so we had this problem where we're like, okay, well, if we want to be optimal, we would use this distribution to sample from, and we need to know this full density here. But the whole point is that we want to estimate p-fail, so there's no way that we could possibly know this density. Okay, so that kind of led to this line of thinking, which was that the optimal proposal distribution is the failure distribution, but we don't know the normalized density for the failure distribution, and that's what we would need for importance sampling. So kind of the next best thing we could do is try to select a proposal distribution that we do know the density of that's as close as possible to the failure distribution. And that's kind of all the innovation that goes on in all the different importance sampling algorithms that we're going to talk about. So really what these algorithms are trying to do is just pick the best possible proposal, knowing that we can never sample from the optimal one, which is the failure distribution. So how can we pick a proposal that's kind of as close as possible that we do know the density of? Okay. So one more note on picking this proposal that I think there was a question about last Tuesday, but I kind of skipped over, which is that we must pick a proposal such that the probability density of the proposal assigns non-zero density to every possible failure. So everywhere that the failure distribution density is non-zero, meaning that a failure is possible for that trajectory, it needs to be possible that we could sample that trajectory from our proposal. So if we just look at this example on the left here, where our proposal is a Gaussian distribution, can someone tell me if this property is satisfied? Yeah, people nodding their heads. Yep, it's satisfied. So a Gaussian distribution assigns non-zero probability everywhere. This is not going to be an issue. Okay, how about over here where we have this like uniform distribution as our proposal? Yeah, no, because there's some region here where the probability density of the failure distribution is non-zero, but we would never sample failures from that region, and so our importance sampling estimator would be inaccurate. Yeah.
Wait, but in some sense that's not a problem, right? Because in this figure, our most likely failure that we're trying to optimize for is still within the distribution.
We're trying to estimate the probability of failure.
Oh, okay. Yeah.
So we need to be able to sample all possible failures. Okay.
Sorry, this is following up on content wave before, but in that case, for the one that in which we're trying to simply, so for trying to estimate the failure, trying to falsify the failure, there's the same constraint. But technically, that's not necessarily like a hard constraint anymore in that case, right?
Yeah, when you're just trying to falsify, you don't have to, like if you're trying to find the most likely failure and you assign zero probability density to unlikely failures, that would be fine. Yeah, just depends on the test. Okay, so back to where we were. So we're going to now talk about a bunch of different importance sampling algorithms and different ways that we could go about selecting this proposal. So one option for this proposal distribution is we could just hand design it. So we could just be like, I kind of know what the failure distribution is supposed to look like. We kind of did that in project 1. And so I'm just going to pick something that I think would be similar to the failure distribution. And hint, hint, maybe your fuzzing distribution that you used for project 1 would be a good thing to start with for project 2 if you want to hand design your proposal. Okay, but hand designing doesn't always work. Sometimes we have very complicated systems. We don't really know what the failure distribution looks like, and it's not super obvious how we could pick something. So it might be a little bit better if we could actually try to do something more adaptive or automatic. And so this other option that we talked about on Tuesday is that we do know how to draw samples from the failure distribution. So that's kind of the last topic that's on your quiz. We talked about how we could use like Markov chain Monte Carlo or rejection sampling to draw samples with just knowledge of what the unnormalized density for the failure distribution looks like. So we do know samples from it, we just don't know how to compute the density. So then we say, okay, well, why don't we just fit a distribution from a model class that we do know how to compute the density of, so for example, maybe a Gaussian distribution or something, to the samples from the failure distribution in hopes that we'll get a distribution that's close to the failure distribution. And then we can use that as our importance sampling proposal. So we looked at how that looked towards the end of class on Tuesday. Here's just another visualization of it. So here we have kind of our nominal distribution over here. We used MCMC to draw samples from our failure distribution. So normally we don't know what the failure distribution looks like. For the simple Gaussian, we can't actually compute it, but in general, we don't know what it looks like. We just have these samples down here. And then we just took all of these samples and we said, okay, let's just fit maximum likelihood Gaussian distribution to these samples. So that's how we get the purple distribution here. And you can see it does, normally we don't get to know this, but it does actually look a decent amount like the failure distribution, which is the red one there. And so we got pretty close to the optimal proposal, I would say. And you can see that in the results where here's the results of doing direct estimation, and you can see that we do much better if we use the proposal that we fit to the samples. Okay, so there's a few challenges with doing that though. The first one is that we saw, we had an entire lecture on how it's a very non-trivial task to actually produce these samples from the failure distribution. So we had to do rejection sampling, or we had to do MCMC, and this isn't, a super obvious thing to do, or it's certainly a non-trivial task. And the second challenge is, let's say we do get samples from the failure distribution. If this failure distribution is high dimensional, so we were just looking at this 1D Gaussian, but remember it could be like hundreds of dimensions because we're talking about full trajectories here. And it could have multiple failure modes. It could be very complex looking. And it might not be so easy to like pick a nice model class and parameters that actually fit all of those samples well. So that's kind of two key challenges with this method. For now, I just want to, there's kind of ways to address both of them, but for now, I just want to talk about this first challenge. And that's that it might be difficult for us to actually draw samples from our failure distribution. Maybe our MCMC isn't working super well, or we just don't want to go through that process. And so let's think of this question like, what if we could still fit a good proposal, but we use samples from a different distribution that's easier to sample from? So we don't draw samples from our failure distribution, we draw samples from some other distribution. And so that's going to lead us to kind of our first topic today, which is the cross-entropy method, Mykel's favorite method in the entire world. It's a form of adaptive importance sampling. And then we're going to talk about something called multiple importance sampling, extend that to population Monte Carlo, which is actually an adaptive version of multiple importance sampling, talk about something called sequential Monte Carlo, and then finally, super briefly, I'm going to mention something called ratio of normalizing constants, but it's an advanced topic, it won't be on any quizzes, so yeah, very briefly, just because I have some good jokes and that's it. Okay, so let's start with the cross-entropy method. So what we were just saying is, we don't want to draw a bunch of samples from the failure distribution, that's hard, that takes up time. Can we just use samples from a different distribution that's easier to sample from and still try to fit a good proposal? Okay, so here's kind of how this is going to work. The first thing that we'll do is we'll draw samples from some initial proposal distribution that's easy to sample from. So something we ideally don't have to use MCMC for, we can just call rand and get samples. Okay, and then, sorry for kind of a lot of text here, but we'll break it down. We're going to use these samples to fit a new proposal distribution from a model class that we also know how to sample from. So this is kind of like another easy distribution. By selecting parameters that minimize the cross entropy between the proposal distribution and the failure distribution. Okay, so let me just repeat that one more time because it's a lot of text. So what we want to do is we have a bunch of samples from some initial distribution. We want to fit a better proposal distribution using these samples. And we'll do that by kind of picking the proposal distribution that minimizes the cross entropy between the parameters for the proposal distribution we pick and the true failure distribution, which is what we ideally would want to sample from if we could. And this kind of minimize the cross entropy idea. So cross entropy is sort of a way you can kind of think of it as almost a distance between two distributions. So if we minimize the cross entropy, we're kind of minimizing the distance between the proposal distribution we're going to use and the failure distribution. And so what we want to do is basically select a new distribution, given all these samples that we have, that gets us as close as possible to the failure distribution, which again was like our whole goal of picking a good proposal. Okay, so let's break down these steps a little bit more though. So we draw samples from some initial proposal distribution that we'll call Q. And then, again, sorry for all the text, this is probably the most text I'll have on a slide this whole class maybe, but I'm kind of breaking down what it means to do this. So it turns out for many common model classes, so for example, the Gaussian distribution that we often use, minimizing the cross entropy is actually equivalent to just computing this like weighted maximum likelihood estimate for the parameters of the distribution. So for a Gaussian distribution, for example, we just weight all of the samples and compute the weighted mean and the weighted standard deviation to estimate the Gaussian distribution from those samples. And those weights are basically equivalent to these importance weights that we've been talking about. So the weight for any sample that's not a failure will be 0. We don't want to fit to things that aren't failures because ideally we want to match the failure distribution. And then samples that are more likely under the failure distribution will have kind of higher weights, also depending on this Q of tau. Okay, so I'm going to show you what all this looks like, so hopefully it'll start maybe making a little bit more sense here. But first, before we do that, we need to pick kind of a proposal distribution to try to start out with. So again, this should be an initial proposal that's easy to sample from. So we need to be able to sample from it, and we're going to need to be able to compute this density Q of tau. So we need something that's easy to sample from and that we know the density of. Can anyone think of a good distribution to try? Gaussian? Yeah, okay. So, and specifically, a Gaussian happens to be the nominal trajectory distribution for the the simple system that we've been thinking about. So yeah, the nominal trajectory distribution, we know how to sample from it, we just do rollouts. And then we also know how to compute the density of it. We just multiply the probability of all the initial states and disturbances that we saw. Okay, so let's see what that looks like. Do you have a question?
Okay, just a higher level question. All this time we've been talking about tau as if it's sort of this distribution that we can easily sort of manipulate. But in reality, there's like many components to tau, and they're sort of conjugate in this giant tuple with a bunch of things in it. Computing, like, is there any considerations in practical, like when we're actually doing this in terms of like practically computing probabilities of stuff and so forth?
Yeah, so we're assuming that we always have a model of P of tau, so we always know the nominal disturbance distribution and the initial state distribution, and the techniques we talked about in chapter 2, where we talk about modeling, that's how we would get that model. Assuming we have that model, we're always able to sample from the nominal trajectory distribution because we just do a rollout using that model. And we're also always able to compute the probability of a trajectory under the nominal distribution.
So is that ever get intractable? Because it feels like for falsification, we do some rollouts and kind of be done, but here we're really relying on sort of P of tau being very easily evaluated, it seems.
I suppose if your trajectories are really long, maybe it'd be an issue, but I think there's a lot of other scaling issues you would run into before that. But yeah, I think as we go through, the methods will get kind of more and more, I don't want to say complex, but maybe more and more involved, and that's because they found problems as you try to scale these things up. And so we're going to talk about better and better ways to do these things such that we can extend them beyond a simple Gaussian. Okay, so here's what we're doing. We drew a bunch of samples from our nominal trajectory distribution, so that's shown here. And then we've reweighted them so that we can try to fit a new distribution to them. So all the samples that are shown in black have 0 weight because they're not failures. And then these are the weights. It turns out they all have the same weight when we use this as our kind of initial proposal. But these are all kind of the weighted samples. So basically what we're doing is we're fitting this purple distribution to these yellow samples because all of the black ones got 0 weight. And so this ends up being somewhat close to the failure distribution, which is nice. And kind of creating this purple distribution that's equivalent to minimizing the cross entropy between this purple distribution and the failure distribution, which we kind of implicitly represent through our samples. Okay, and so we can see now that this has worked pretty well. So for direct estimation, it doesn't, it has this big variance, and then similar to what we've seen before, we get a much lower variance and more accurate estimate when we use this proposal that we fit. Okay, so that's all working well for this kind of threshold of -2. You can imagine if we decrease the threshold, failures will become more rare, so we're going to get fewer and fewer samples that we can use to do this fitting. And let's kind of keep decreasing it here. Okay, so I'm just going to tell you right now, for the next time step, or for the next decrease here, we're going to end up with no samples that lie within the failure region. So what do you think is going to happen to the algorithm? Yeah, there's like, you can't do anything, so. Okay, so yeah, we're kind of in trouble now. From here on out, we don't have all of our weights are zeros, there's just nothing that we can do. So this didn't work so well. So again, we're kind of having this issue that comes up over and over, which is like if we start with a nominal distribution, we're having all of these issues now when we have more rare failures.
In reality, do you like fix the number of samples? You just keep sampling until you have a sufficient support for the cross entropy?
So you could just keep sampling until you have a sufficient support, but I'm going to show you a technique right now that'll be much better. Okay, so basically what we just saw was that if we sample from the nominal distribution and failures are rare, then we might not get any failures, and then all of our weights are 0, and we're like, we don't know what to do. Okay, so one thing that we could do is we could start with the nominal distribution and try to kind of iteratively adapt it to move closer to the failure distribution. So rather than trying to make this big jump all in one, we start with the nominal distribution and we take smaller jumps to make our way to the failure distribution. So let me show you how to do that. And by the way, this is why it's called adaptive importance sampling, because we're going to adapt this proposal distribution. So here's kind of how it works. What we do, before we start, we pick an initial proposal distribution to adapt. So maybe that's, for example, our nominal trajectory distribution. And then the other thing we're going to need to do for this method, similar to what we've done in the past, is we need to pick some notion of closeness to failure. So again, in this case, we could just use, for example, the robustness. So maybe for like some sample trajectory, the distance to failures, or closeness to failure, is just going to be this distance to the failure region. And we're going to add one more requirement to this function f of tau that gives us our closeness to failure, which is that f of tau needs to be less than or equal to 0 for all failure trajectories. So that way we can rewrite this p tau given tau's a failure as p tau given tau, f of tau is less than or equal to 0. So we're just saying these are now equivalent conditions in terms of f of tau. And it'll be clear in like a minute or two why we want to actually write it like this instead. Okay, so this is kind of our failure region now, and we know that every trajectory in this region will have an f of tau that's less than or equal to 0. Okay, so that's kind of our setup. And ideally, what we want to do, what we were just trying to do before, is we want to minimize the cross entropy between this distribution and our failure distribution. So between this distribution and this p tau given f of tau less than or equal to 0, which is our failure distribution. But we just saw that if we draw a bunch of samples from this distribution, it's possible that all of the weights are going to be 0 because we didn't get any samples from the failure region, so we're not actually able to minimize this cross entropy. So this is kind of what we do instead. So we're going to take an iterative process now, where at each iteration, we're going to draw samples from the current proposal. So we have samples now from our nominal trajectory distribution. And then we're going to compute f of tau for each of these samples, so each of their distance to failure. And then we're going to pick the top m elite samples. So m elite is just some number. It's like a hyperparameter of the algorithm you need to pick. So I think here we're taking like the top 50 or something like that. And so we're going to just look at what are the top 50 objective values. And then we're going to set a threshold based on the highest objective value of all of those. So we're going to look at kind of like what is the worst elite sample, and we're going to pick a threshold gamma to be there. And then what we're going to do with that threshold is now, instead of computing the cross entropy or minimizing the cross entropy between this distribution and the failure distribution, is we're going to relax that assumption a little bit. And we're going to say, instead, let's minimize the cross entropy between this distribution and p of tau, given that f of tau is less than or equal to this threshold. So it doesn't need to be less than or equal to 0. It doesn't need to be a full failure. It just needs to be a little bit closer to failure. And so we've kind of defined this new threshold that's maybe kind of a relaxed version of this problem here. So now we know that for sure we're going to have samples that have non-zero weight because we've picked the threshold to have at least m elite of these samples. And so we can fit our distribution to this set of samples now. So that's what we do. We just fit the next proposal distribution using the weighted maximum likelihood to that set of samples. And then now we're getting a little closer to the failure distribution. And if we just keep repeating this process, ideally we'll get all the way to the failure distribution. So we'll repeat, we'll draw samples from this distribution now. We'll compute the threshold based on these elite samples. We'll weight them and then fit a new distribution. And we can just kind of keep doing this for some number of iterations. And then eventually we'll end up with, we could look and see if our threshold becomes less than 0. That means we've got enough failure samples to kind of fit to the failure distribution. And then we end up with some kind of final distribution. Yeah.
So I guess like the idea is that you just keep on moving like the gamma all the way to the left until you get to like the failure, right? And then you just like entirely cover the failure region.
Yep, yeah, exactly. So the question was you just kind of keep moving gamma to the left until you get to the failure region. So that's exactly right. And I guess specifically it's to the left for this example. The more general idea is you're like making, requiring that you be closer and closer to a failure, whatever your closeness metric is. So for like the pendulum, that might be like, you're closer and closer to falling over or something like that.
Just guarantee that you're going to move closer to failure every time, or not necessarily?
I don't know.
It's a stochastic algorithm. You can get unlucky, and there's no guarantee.
True. We could get samples all the way over here and then fit a distribution over here.
Be very unlucky.
Well, I guess you get all zeros there, but yeah.
By the time that we hit the failure, or in sort of the failure region, do we ever convert our weighting back to the binary objective of failure or not? Or do we always keep losing gamma?
I think you want to. You never want your threshold to become less than 0. Is that the question you're asking?
You never want your threshold to be less than 0?
Yeah, because if you make your threshold be like, let's say like we put our threshold over here, then we're going to fit a distribution over here. But that's not going to be a good proposal distribution for important sampling.
Sort of then cap it at 0?
You cap it at 0. Yeah, that's kind of a detail I didn't put in here. But if you look at the implementation in the book, you'll see that we actually max it with 0. Yeah.
Does your effort
Yeah. I have to think about that.
Imagine it would get stuck if it does anything like that. If it's not monotonically increasing, then if you're selecting, it would get stuck. Imagine like paraboloid or something. Or sorry, a hill, an inverted paraboloid.
I'll have to think about it because you're drawing like a lot of samples, so you might get over one of those hills.
So you're selecting like the N elite and your top 10. And if it's not monotonically increasing, then the direction of travel will not be guaranteed. If it's a cosine curve, I can select it anywhere.
Nothing's really guaranteed, but you can imagine a failure definition where tau has to be the absolute value of tau has to be greater than 4. And so you can have 2 different failure regions.
Right.
So you might naturally go to 1, but you can use a different proposal distribution, like a Gaussian mixture.
Yeah. Does that kind of answer your question?
But I still think the issue is not solved because there has to be some guarantees on f of tau. If you make your f of tau to be cosine, and you're setting samplings to N elites.
Well, it can't be cosine because you need this requirement such that it's less than or equal to 0, and it's a failure for all failures. I'll have to think about it and get back to you. Typically, when you're using robustness, you don't have an issue, but and that's typically what people use. But in general, there might be other constraints on that function. Was there another question over here?
It was just a similar question. Like, could you fit a multimodal distribution, or do you, whenever you fit the distribution, do you like change the type of distribution that you fit from iteration to iteration?
Yeah. So the question is, could you fit a multimodal distribution? And that's exactly right. So if you have multiple failure modes, then you probably would want to fit a multimodal distribution. So imagine there was like another threshold over here. Then our elite samples are going to be like over here and over here. So we're going to have these like 2 groups of samples that we want to fit a single distribution to. And so we're probably going to want to fit like a mixture in that case. Okay. So yeah, once we're done, we just take our final proposal that now looks pretty good. It looks kind of like the failure distribution, and we'll perform important sampling with this final proposal. And just by the way, because we know what the failure distribution for this system looks like, we can actually see how well we did, and you see we get pretty close to the failure distribution in Gaussian form. So kind of as close as we can get if we're fitting a Gaussian distribution to things. Okay. And then just kind of one other way to visualize it. So we've now graduated from 1D Gaussians, and we're moving up to 2D Gaussians. So this is a similar problem, though, just in 2 dimensions. So our nominal distribution is a Gaussian that's centered at the origin here with 1 covariance of the identity matrix. And then our failure region is up here. And as you can see at this first iteration where we just draw samples from our nominal trajectory distribution, none of the samples overlap with the failure region. So we pick the elite samples that are as close as we can get to the failure region. And then we kind of iteratively continue to adapt this threshold until we make our way to the failure distribution. Any Any questions on that?
Sorry, wait, but this is not good, right? Because this is not even covering or not even close to the.
Yeah, good question. So the question was, this doesn't look good because it's like barely in the failure distribution. So I'll show in a minute like a little more about this problem because we're going to use it again. But like the nominal trajectory distribution for this problem is centered here with like unit variance. So the contours are going like this. So actually like the failure distribution at this point, like it's very high likelihood here. Well, I wouldn't say very high, but like highest likelihood here and like much lower likelihood out here because you're even further away from the origin.
So we're trying to actually estimate the probability is negligible whether or not we do the rest of it.
I don't know if you can say that for sure, but like in general, yeah, like you want to, the failure distribution is very concentrated at this corner. So we are doing a good job. Cool. So that's the cross entropy method. All right, so the next topic we're going to go back to, we're going to stop adapting things for a little bit and just go back to another version of importance sampling, and that's multiple importance sampling. So we're back to this whole like indecisive thing that I've talked about before, where like, you know, for regular importance sampling, we have to pick a proposal distribution. We only get to pick one, so we better choose wisely. Or we could just do multiple importance sampling, and we could just pick many proposal distributions, and we don't have this issue, which is perfect for me because I'm, again, super indecisive. Okay, so that's really all that's going on in multiple importance sampling is like we just do the same thing, but with multiple proposal distributions. So the steps are going to look very similar. Now we just draw samples from all of our current proposals. So each I represents like a different proposal. And specifically QI tau would be the proposal used to generate trajectory I. And so for example, let's say we have two proposals like this. So you could have more than two, which we'll see in a minute. But let's just say we have Q1 tau and Q2 tau. And we're just going to draw samples from them. So maybe we'll just draw a bunch of samples from Q1. We'll draw a bunch of samples from Q2, and then now we have samples that we can use to estimate our probability of failure. And then we're going to estimate our probability of failure from these samples in a very similar way, in that we're just going to take this weighted sum, and the weight calculation is super similar. All we do is kind of almost exactly what you would think. We compute its density under the nominal distribution, and then we compute its density under the distribution, or the proposal that it was sampled from. So the only difference here is just this I here. So we just make sure that we're computing the density under the distribution it was sampled from.
I think it's not updating.
Oh, that's weird. Now it is. Oh, very strange. Okay. So here it is in a square. So again, we're taking this weighted sum, and the weights are the density under the nominal distribution divided by the density under the proposal that it came from. And we call this standard multiple importance sampling, or SMIS. It turns out, in kind of this crazy fashion, there's actually another way that you could do this weighting that's equally valid. So this kind of took me a minute to understand in my brain, so we'll see how it goes. But I think it's kind of interesting to think about. So what's going on here is when we think about standard importance sampling, we're assuming that this data, these sample points, came from a specific process. And that process is that we started with one of our proposals, so Q1 tau, and we drew a bunch of samples, so this is what we saw before. Then we went over to Q2, and we drew a bunch of samples from Q2, and then we get weights kind of the way we would expect. But now there's also another option, or another way that this data could have been generated, which is like this. So what we could instead do is say, at every time that we're going to generate a new sample, we're going to pick randomly between Q1 and Q2. Let's say that we pick Q2. Then we're going to draw a sample from that distribution. Then when we draw the next sample, we're going to pick randomly between the two. Let's say this time we pick Q1, and we draw a sample from Q1, pick randomly again, draw a sample from Q2, and so on until we get all of our samples. And the idea here is that this process that I just showed you is actually equivalent to sampling from a mixture model of Q1 and Q2. So we'll call this Q mix, and it has this density. And so we could also say that all of these samples were actually sampled from this mixture model. And it turns out that if we do this, we actually get a different weight that we would want to use for our importance samples. And it looks like this. And it's actually considering the full mixture of those distributions when we compute the density of the sample. And this is kind of crazy, like both of these estimates work. But it turns out that actually if you do it this way, where you assume it comes from this mixture model, it's been shown to have lower variance. So sometimes it can perform better. Yeah, I don't know. This was totally not intuitive to me at first. Yeah.
Wait, so is it basically just the same, but you have like different weights?
It's the same, but you have different weights.
Okay.
Yeah.
I think we're using I. So I
That's
is
true.
sampled and
Yeah.
Q,
Good
so it should
point.
be
I'll
J.
fix that. Yeah. We should have a J.
So everything in the sum is J.
Everything in the
Okay.
sum is
Makes
J.
sense. Very cool.
Well, the tau is I. The Q is J.
That's true with the top one too, it should be QJ.
The top one should be QI.
You don't have number of distributions equal to number of samples.
You do.
You have exactly.
Well, like QI could be like Q1, like Q. Let's say I took the second sample from
I understand.
Q1, then Q2 is equal to Q1. Sorry, that was a really confusing way to say it. But
And
that's
then you
what's
would
it.
have like tau 1, tau 2, tau 1, tau 2, tau 1. You could have ends, you could have 3,000 samples with all samples.
Yeah, that's fine. And then like the first half of them are from one, and yeah.
This is what we need to yank out the superscript notation.
Yeah, we were trying to mess with notation earlier in our meeting for the book. It's not an easy thing, that's for sure.
Check your Slack. Wait, sorry. Can you clarify once again what is what in terms of which tau?
Yeah. So here, let me write it out. This should be a J, and that should be a J.
Yeah, sorry.
Do that. I'll make sure I fix these before I post the slides.
Top is the I's from the distribution you came
From the distribution you came from. Tau I came from QI, and QI could be Q1, it could be Q2, it could be I don't know, whatever it was.
Yeah, sorry. I was just to clarify, like compared to like SMIS, like the first sampling part using like a Q1 and Q2, is that kind of like, do we just like follow the same procedure? And then when it comes to like applying the weights, we just kind of like perform the summation over the two distributions?
Yeah, so this is a great question. So the idea is like the procedure for sampling doesn't necessarily change, but we can, once we have the samples, we can assume that they came from any procedure we want. So basically the second one is assuming that they came from the second procedure that I showed you, and the first one is assuming they came from the first procedure, and they're equally valid assumptions.
Okay, so like we can, so the summation essentially just creates like the mixture distribution. We have to
Yep.
go with like Q1, Q2.
Exactly, you don't have to like actually sample that way. Yeah. Okay, so yeah, so this was kind of super unintuitive to me at first, so no worries, you have to go back through it a few times. But so we'll go back to this 2D problem, and now we have two failure modes. So we have the upper left corner and the upper right corner. And we see the nominal trajectory distribution is just kind of this Gaussian distribution that's centered at the origin. And then the failure distribution is just going to be that kind of cutoff. So again, like you see, now I'm actually showing the failure distribution. We have much higher likelihood at these like front corners here. So that's where we'd want to be sampling from to get a good estimate of the probability of failure. And so now we can look at what this looks like. So if we wanted to only pick one important sampling proposal, and let's say we wanted it to be a Gaussian distribution, then we're going to have to pick one that's kind of big enough to cover both of these failure modes. But if we now have the opportunity to pick more than one important sampling distribution, we can kind of spread them out to cover the regions that we think are important. So here we've now picked a few distributions that sample from those regions that we think are important. And it turns out that if we do this, we could generally do a little bit better than regular important sampling. So you can see it's kind of hidden behind in gray there, but the regular important sampling estimator has this kind of big variance over here. And then you can also see what's really interesting is, like we said, sometimes this deterministic mixture assumption can actually do better than the standard multiple important sampling. So if we weight it according to the deterministic mixture, we get this line here. Okay. So that's multiple important sampling. So when we looked at the cross entropy method, we saw that we had trouble kind of picking our own important sampling proposal where we just had to pick one. So we were like, let's pick one and adapt it. We're going to do the same exact idea, but now with multiple important sampling. So we might be like, okay, we now get to pick more than one, but that's more things we have to choose. How are we going to choose all of those proposals? And so what population Monte Carlo allows us to do is take multiple importance sampling proposals and adapt those to get a better set of proposals. Okay, so the key idea here is like, let's adapt a whole population of proposal distributions. Okay, so first I'm just gonna kind of visually show you what this looks like, and then I'll show you the actual like steps of the algorithm. But basically what we do is we start out with a whole bunch of proposals. So like every single one of these, like this is like one distribution, this is another proposal, this is another proposal, and so on. So we have this like whole set of many proposals. Oops. And then what we're gonna do, the first step that we're gonna do, is we're just gonna draw a sample from every single one of these proposals. So each sample, or each proposal, we just get one sample from. So here's like our sample from this proposal, and so on. And now we're left with a bunch of samples from our proposals. And the next thing that we're gonna do is kind of weight these samples according to their importance weights. So any sample that's not in the failure region is just gonna get 0 weight. And then the samples that are in the failure region are gonna be weighted according to that P over Q. So P being what its weight, or what its density is under the nominal trajectory distribution. So that's why you see kind of brighter values where the nominal distribution will have a higher density. Divided by Q, which would be the density that from the proposal that it came from. And then what we're gonna do is we're actually going to resample these samples according to these weights. So we're never gonna get any new samples outside the failure region because they all have a weight of 0. And then we're gonna be more likely to resample points in areas where they have a high weight. So that's kind of what this looks like. And it looks like we just kind of decreased the number of samples a ton. We didn't actually decrease the number of samples, but they're all kind of on top of each other here because we've resampled the same amount of samples, but from a distribution where it was more likely to sample something with that had a higher importance weight. So this might be like 5 samples all on top of each other here. So we still have the same amount of samples, we just have, we've just resampled them. Yeah.
Sorry, where did so these are all samples, not distributions.
These are all samples.
So we had a bunch of distributions fly around, how do we know what's going to correspond to what distribution? Or how many to sample from each distribution?
I think you can decide how many you want to sample from each distribution. So at this step, we just sampled 1 point from every distribution.
Right, but then so 2 steps later, now you have a bunch of points, and you can fit the same number of distributions out. Like, you see what I mean?
Well, I haven't finished the algorithm.
Oh, okay, got it. Sorry.
I think you'll see in like probably exactly right now. So now we have a bunch of new samples, and all we do is put new proposals, like kind of slap new proposals on them. So we just say maybe our new set of proposals is going to be centered. Each proposal is going to be centered at our sample with some constant variance. So all we did was take all the samples here and turn them into proposals by saying we'll just make a new proposal where the mean of that proposal is the sample that we had, and we put maybe some constant variance with them. Okay, and so now we're back to where we started, and so you can imagine we could repeat this process and continue to try to kind of improve these proposals. But already this is looking pretty good, because if you remember these kind of proposals that we hand designed for this same exact problem looked like this, and we're kind of have already automatically found a very similar set of proposals. So this might work well. Okay, so let's put some actual steps to what we just did. So again, we start with some initial population of proposals that's spread out over the entire space of possible trajectories. And one note that I want to give here is that it's very important that this initial population of proposals cover the space of possibilities as best as possible. Because if we never have any samples in the failure region, then all our weights are going to be 0, same problem as before, and we're not going to actually find anything. So we need to make sure, and this is a non-trivial thing to do, this can be very difficult. So we need to make sure, though, that we pick a bunch of proposals that will cover the space of possibilities. Okay, and then after this, we drew a sample from each proposal. And then we computed the importance weight for each sample. So that was that P over Q multiplied by the indicator function. And then we resampled based on those importance weights. So we were more likely to get new samples where the importance weights were high. And then we just kind of slapped on a new proposal to all of our new resamples. So again, it's not like we decreased the number of proposals, they're just kind of on top of each other. Yeah. And then we can, like I said, repeat this until we're satisfied for some set number of iterations. And then once we're done, we will take these proposals that we ended up with and perform multiple importance sampling with them to try to estimate our probability of failure. Any questions on population Monte Carlo? Yeah.
Each accepted sample, we add some variance that we allow for the resampling process, and that variance that we allow for the population is like a heuristic or something?
Yeah, exactly. So the question was like, so for each sample we have left, we now make these new distributions, like how do we pick the variance we're gonna put on them? Yeah, it's kind of a hyperparameter. So you don't even have to make it Gaussian. You could, it's kind of up to you how you wanna take a sample and turn that into a distribution, but one very straightforward way is to just say that it's a Gaussian distribution centered at that sample with some constant variance. You can imagine that, the bigger variance that you pick, maybe the more exploration of the space you'll get, but then there's kind of this less exploitation because you knew that that sample was good because it had a high weight. So yeah, it's something you kind of have to balance. To like decide the parameter? To decide the parameters, everything. Yeah, you could do some like any hyperparameter optimization. Yeah. Okay. So now we're going to extend population Monte Carlo to something called sequential Monte Carlo. And so the idea with sequential Monte Carlo is with population Monte Carlo, we had all these samples, but we were still maintaining these like explicit distributions around them. So we still had these Gaussian distributions that we like had a density for and everything. And it's not always super easy to do this. So like in general, when you have very complex failure distributions, you might not want to maintain like these very specific parametric distributions like Gaussian distributions or something like that. And it kind of gets to that second challenge we talked about at the very beginning of lecture, where it's not super easy to just like fit a distribution to a set of samples from a very complex, multimodal, high-dimensional failure distribution. And so maybe what we want to do instead is just take a bunch of samples, and now we're only going to keep track of samples. We're never going to actually like pick some type of like Gaussian distribution, anything like that. And what we're going to do is we're going to try to move samples from the nominal distribution. So we have a set of samples that we took from the nominal trajectory distribution, and we're going to try to move those to the failure distribution. And it turns out that we can estimate the probability of failure based on the path that the samples take as we move them from the nominal distribution to the failure distribution. So this might all seem like magic right now. I'm just going to very slowly go through kind of how we do this. Okay, so typically the way, let's start with just like how do we have a bunch of samples from the nominal distribution, how do we like move them to the failure distribution? Like what's going on there? And typically what people do is they move samples through a series of intermediate distributions. Okay, and so then how do we get a series of intermediate distributions that go from the nominal distribution to the failure distribution? It turns out we can use this idea of smoothing that we used when we were doing MCMC. So let me show you what that looks like. What we want to do is we want to move from the nominal distribution to the failure distribution. When we first introduced smoothing, we actually kind of went the other way. So we said when smoothing is 0, our distribution is exactly equivalent to the unnormalized density of the failure distribution. And then we said, as we increase the amount of smoothing, we kind of start to assign non-zero probability. So we're increasing that epsilon value, that variance in the normal distribution that we use to replace the indicator function. And we said, as we kind of keep increasing it, we actually move from the failure distribution to the nominal distribution. And so our goal here is now kind of the opposite. We want to go from the nominal distribution to the failure distribution. We want to find a series of intermediate distributions in between the two. So we can just do this in reverse. So we just start at infinity and slowly decrease this epsilon parameter until we get to the nominal distribution. Show that one more time. So this is kind of a series of intermediate distributions that gets you back to the failure distribution. Let me say that backwards. We can also do this in 2D for our 2D problem. So here in 2 dimensions, we're trying to get from the nominal distribution, which is this Gaussian that's centered at the origin, to the failure distribution, which looks like this up here. And we end up getting kind of these like teardrop-shaped intermediate distributions if we just apply this smoothing, where we kind of move from one to the other. Can show. Okay. Cool. Any questions on that? Yes. No.
It's like magical, so it,
Oh yeah, yeah, it's pretty cool, right? It's yeah.
well,
It's,
no, in the sense of I'm not sure what's going on.
oh, you're not sure what's going on. Another way to have magic. So, does this one make sense? Or?
No, like number goes down and distribution moves. Like that seems very.
So this number though is that the variance. And remember how we replaced the indicator function with a Gaussian normal distribution that was like had this kind of small variance, and we said as we move the variance, so we're doing this normal distribution with small variance multiplied by the nominal distribution, and as we increase that variance, we actually go from the failure distribution to the nominal distribution. Okay, let me check out
There it is. Yeah, can you have the equation of it somewhere? Okay, there you go.
I don't know how this is feeling. Well, okay, ignore the normalization. That's just to get the values to look good. But there you go. So this is the nominal distribution,
Yeah, that's.
and then this is that smooth version of the indicator function, where epsilon is the variance of that.
Oh, I see. Okay, great. Thanks.
All right. See, this is a great ad for Pluto notebooks. The code's right there, as messy as it might be. Yeah.
So doing the smoothing, I guess, relies on us being able to kind of soften up this constraint with this like indicator function thing. But that kind of implies that always we can define having a failure, not just in a kind of binary sense, yes, no, but like give it an actual number that we can loosen up, right? Like, is it like, do we kind of always assume that the failures are numerically, like, do we can kind of assign a value to the failure and not just say, yes, this is a failure, this is not a failure?
Yeah, that's a great question. So typically what we use for that is robustness. So anything you can write down in signal temporal logic, you can define that value for. But yeah, in general, if you can't write down your specification that way, then maybe it won't be as straightforward how to like pick something that gives you that property. Okay, so here's kind of what we just showed, but now I'm actually showing all of the intermediate distributions in between, or we've picked, some set of epsilons that will give us this nice smooth transition from the nominal distribution to the failure distribution. There is one other way to do this that's, way less cool, seems way less like magic, but it also works well, which is similar to what we were doing in the cross-entropy method, where we specify kind of this threshold on the distance to failure, and then we just decrease that threshold as we go. So that's another way that you can also do this. Okay, so now we talked about how we get this series of intermediate distributions. How do we actually go about moving samples from one distribution to the next? Because we're going to start with samples from the nominal distribution, and we need to figure out how we can move them from the nominal distribution through all of those intermediate distributions. And it turns out that for these intermediate distributions, if you remember when we applied smoothing, we just applied it to the unnormalized density of the failure distribution. So all of these densities for the smooth distributions are also going to be unnormalized. And how do we sample from unnormalized distributions? Well, MCMC, of course. So we're going to do this using Markov chain Monte Carlo. Okay, so let's say that we've picked out our intermediate distributions. So we picked a few different values of epsilon, and we've gotten these smooth distributions now. And so we want to go from samples from this distribution, which is the nominal one. We know how to draw samples from this distribution to through these series of intermediate distributions to the failure distribution. Okay, so now let's say that we just want to look at this first step. So we want to go from this blue distribution to this kind of like purplish one. And so what we do is we get our samples from the blue distribution. So again, we know how to get these from the nominal trajectory distribution. And now what I'm about to show you is imagine for each sample, so let's say we just started this sample here. We're going to kick off an MCMC chain from this sample with this distribution as the target distribution. So you can imagine it's going to kind of wiggle around for a while and eventually kind of move itself to these more high likelihood areas of this distribution. And we're going to kick off a different MCMC chain for every single one of these samples. And we're going to do some number of iterations for that, and they should kind of slowly wiggle their way to being samples from this distribution here. Okay, so let's see what that looks like. Pretty cool. Maybe we'll see it one more time. So what's happening is that each of those kind of movements is one MCMC step for those samples. And then that was just 50 MCMC steps. And now these samples appear like they come from this intermediate distribution here. Now we want to get to the next distribution. Just do the same thing. So kick off an MCMC chain from each one of these samples with the density of this distribution as our target density. That's deciding, whether we accept or reject these samples. And we just do it all again. Yeah?
So when you say kick off some samples, do we sort of fit a distribution to these and then resample and then kick off some of those? Or do we just take what we had that's already moved and then just keep moving them?
In what I'm showing you now, we just take what we had and we just move them.
Okay.
There is actually often people do this resampling step, which I'm going to talk about in a second, where it generally makes the MCMC more efficient if you do some sort of resampling. But for now, we're just saying we took some samples, we kicked off an MCMC chain with this as the target distribution. Then we took those exact samples we ended with and kicked off another chain with this now as the target distribution.
And in theory, we can also just not smooth it, just kind of try to sort of have a giant, sort of not a jump, but in case the density is non-zero throughout the entire space, then we can also just hope that MCMC will get there by itself if we didn't do any of this, right?
Yeah, so we don't technically have to smooth it. We could just go straight to the failure distribution, but MCMC is going to be a lot less efficient.
Makes sense.
Here you need to pick a sequence of epsilons that define each of the different smoothing distributions. It seems to me in general quite difficult to pick the right sequence or a useful sequence of epsilons if you don't know a lot about your kind of situation. Does it sound about right?
Yeah, the question is how difficult is it to pick them? Would be a good person to talk to about this. He has more experience with trying to do this, but I think in general, you can at least look at how you did. You can look at the samples by the end. I'll show an example with the pendulum, and you can see if your samples towards the end are starting to move towards failures. You can at least look at the samples that you're getting, and if you find that there's this huge jump between the last step and your actual failure distribution, then you probably need to repick epsilon. So there's ways to at least kind of guess and check. Okay, so then we have one more step to go through. So we'll just, again, start with all of these samples and do a bunch of MCMC steps. And now we've kind of made our way to the failure distribution. I think there's one more step that I didn't show, which is now you actually do it with the failure distribution as the target, but I don't have the animation for that. Okay, so then we have all of these samples. Okay, but we're trying to estimate the probability of failure. So how do we actually estimate the probability of failure from all this? And so like I said, it turns out that we could look at the path that each sample took and get an estimate for the probability of failure. So what I'm going to do now is I'm just going to label these intermediate distributions. So G1 is always going to be our nominal trajectory distribution. And then Gn, in this case G5, will be the failure distribution. And then it turns out what we do is we keep track of a weight for each sample. So we initialize all the weights to 1, and then every time we make a transition, we keep track of a weight that's basically the previous weight times the likelihood under the new distribution divided by the likelihood under the old distribution that we were coming from. It's not obvious that this works at all, and it turns out we thought about including the proof in the book, and it was very involved. So if you're interested in where this all comes from, there's a reference in the book to a paper that you could read more thoroughly, but this is definitely not obvious. So this is something you're just going to have to believe me on or go look up that paper. But it turns out that if we then average all of the weights at the final iteration, so we've gotten here, we've kept track of a weight for every sample, and we take this average of all the weights, we actually get an estimate of the probability of failure. Okay, so that's our estimate. So a few notes on this. So one, as you were kind of asking about earlier, it's actually very common to do a resampling step, similar to the resampling that's done in population Monte Carlo for each transition. And if you want to see how that's done, there's a nice example in the book that visualizes this. Basically, it allows us to move our samples to the next distribution in this kind of resampling-based way before we do MCMC, and so it might make the MCMC more efficient, so we don't have to do as many MCMC steps to transition from one distribution to the next. So this is a very common thing that people do. Okay, another thing that I think is like a really big thing to highlight here that I was talking about earlier is like SMC is non-parametric. So we didn't like pick any parameterized distributions for any of this. We did everything with samples. And what's really cool about that is if we have these very complex multimodal failure distributions, we don't have to try to fit some complex distribution to it with some parameters. We can just maintain a bunch of samples to represent that very complex distribution. And so to kind of highlight that, let's move from our 2D Gaussian to this pendulum example, which is like around 50 dimensions. So each sample now is a trajectory. And what we do is we've picked this kind of series of epsilons, and we've slowly moved samples. So these were the initial samples, and we've kind of slowly moved them towards the failure distribution using this MCMC. Cool. We might finish early today. All right, so we've kind of gone through all these things, and now I'm going to talk super, super briefly about this ratio of normalizing constants idea. So this is basically the only kind of legitimate thing I'm going to tell you about this. And this is an advanced topic, unfortunately. But it turns out what's kind of really interesting is that importance sampling, everything I just showed you, is actually a special case of a more general problem of determining the ratio of normalizing constants between two distributions. So this should sort of make sense to you because I said that the probability of failure is the normalizing constant of the failure distribution. So there's one normalizing constant. And it turns out if you can determine this ratio and do it in a certain way, you could actually, you actually kind of land on the importance sampling estimator. But if you view it as kind of a more general problem, you can derive other types of estimators, which is really interesting. So if we step back and say, let's move away from importance sampling, let's think about the general problem of determining these ratios of normalizing constants, you can derive a bunch of different types of estimators. So ones we talk about in the book are like self-normalized importance sampling, and bridge sampling, and umbrella sampling, and they're all super interesting. And yeah, so this is me right now because I absolutely love everything we wrote in the book about this. I think these concepts are like, they require a lot of distilling from very academic mathy papers, and I think we did a really nice job of it. So if you are interested in these topics, do check them out. But we're back here and we have too much to do and not enough time, so we don't get to do this. And so I really wanted to show it all to you, but we don't get to. But there is one figure specifically in the book that is particularly special to me, and that's figure 7.12. So some of you already know where this is going. So this is the optimal proposal distribution for self-normalized importance sampling when we're doing something similar to umbrella sampling. And that's not all supposed to make sense to you, but what's interesting about this particular figure is that about like kind of early last year, I was designing invitations for my wedding, and I was visiting my mom in San Diego working on these invitations, and so should come as no surprise to you that I wanted a dark theme wedding invitation, especially at this point. I think this is pretty clear. So I started designing a dark theme wedding invitation, and I was really excited about it. And then my then fiance, now husband, walked by while I was doing this, and he was like, absolutely not. This looks like an invitation to a funeral. We can't have a dark theme wedding invitation. So I was like, oh, bummer. And then I was working on specifically this figure at the time, so I just went back to my work on the book. And then my mom walked behind me, and she was like, oh, that looks pretty cool. Like, why don't you just do that? And so unbeknownst to probably 99% of the guests who attended my wedding, the optimal self-normalized importance sampling distribution was actually on my wedding invitation. So yeah, it's probably one of the few people to have PGF plots on their wedding invitation. And yeah, I think my other point here is like, if for some reason the book isn't that enticing to you, one, bummer, but two, no worries, the figures also make good decorations, so you can try it out yourself. Okay, that's it. That's all I have today. We're going to wrap up early, I guess.